So we just discussed what is the work of expansion and what is the work of compression, and we are only discussing the work as pressure volume work, which is associated with expansion or compression of a gas. Now, how it will look like on a diagram? If we want to diagrammatically represent how the pressure and volume are changing and what is the work done, how will we represent it? Remember that it's a multiplication of two terms, pressure times change in volume. Now we said that our system is exchanging heat with the surrounding, which means the temperature was kept constant, which again means we are going to draw how the work done will look like in a PV isotherm. So we are going to show now the graphical representation for work done for compression and for expansion. We'll start with expansion. So what we showed in the previous examples is called single stage expansion and single stage compression. By single stage we mean that we just put the weight and removed the pins, and then the piston moves in one step so that the volume changes from some initial volume Vi to a final volume Vf. However, we could have done it in the multiple stages. First, let us look at how the single stage expansion look like in a PV isotherm. Now let us once again draw it. This was the expansion, which means initially the volume was like this and the pins were attached. Suppose this is the mass M, and then there's another set of pins. All of a sudden we remove those pins so that the system expands until and unless the piston touches these pins which are lying above, and this is the final stage. So this is the change which we discussed when we were discussing the definition of terms. This is the change of the system, and of course there is an associated change in the surrounding, because you see that this mass has been lifted now during the expansion work by the system. Now initially, suppose the system had a pressure Pi and Vi, and then finally we are calling it as Pf and Vf. So let us try to draw an isotherm, pressure versus volume, for a constant temperature. And you know that if the gas behaves ideally, then the state must lie on somewhere on this isotherm, because this isotherm represents the states of the ideal gas at a definite temperature. So while we made this change, we have somehow moved the system from some point to some other point. In this case, remember, it's an expansion work that we are discussing, so the volume should increase, which means the initial volume was smaller or initial pressure was higher. Suppose this was the initial state, which were defined as Pi and Vi. So Pi is the corresponding pressure and Vi is the corresponding volume. Now what we did is that we expanded the system to a final pressure which is Pf and a volume which is Vf. Now this was done against an external pressure. Now what was that external pressure? Here let us try to understand that this mass is creating a pressure which is the external pressure. Here also it is creating this pressure which is the external pressure, which was constant throughout the change of this system. Now this P external which was exerted on the system, here it may be equal to the pressure of the system itself, which is PF. In that case we do not need these pins because the pressure inside and pressure outside will be just equal, so the piston will be nicely balanced. But the way we have drawn it is that we have kept the pins, meaning that this PF is still slightly higher than the P external. So P external is somewhere here, meaning if we remove these two pins, the gas can still expand a little bit and go to a point where this final volume, which we denote as say another VF prime, this pressure of the gas will be equal to this pressure, which is the external pressure. Remember, this external pressure was constant throughout, but the pressure of the gas is changing from Pi to PF to say PF prime. So we can think about two different situations, but let us first confine this situation where the pins were intact and the pressure of the gas was slightly higher than the external pressure. So the external pressure is somewhere here. Now what is the expression for work? The expression for work says it is negative of external pressure into V final minus V initial. Now what is V final minus V initial? This is this length, and if we multiply by P external, which is this, we are basically talking about an area which is this. So the work done in this case is nothing but the area under this region which I have shaded. So this area is nothing but equivalent to the work done in the process. Now imagine another case which we just said that we'll let the system evolve until and unless the pressure becomes equal to the external pressure. So the external pressure were somewhere here. Let us just draw the isotherm. Okay, so the external pressure is somewhere here, which we denote as Pext, and this was our P initial. This is the initial state, and this was the corresponding volume for the initial state, which was Pi. And now see that the final state, which we denoted as Pf prime, is slightly shifted, as you can see from here, because if you compare the picture on your left, in the earlier case Pf was here and the work done was something like that. However, the corresponding pressure P external was less than the actual pressure of the system, which was Pf in the earlier case. So we assert here that we are also removing these two pins, and what happens? Then the piston moves, and until and unless this external pressure and the final pressure gets adjusted, the piston moves, and when the final pressure drops to the external pressure, there is an equilibrium, so the piston doesn't move. So the gas again expands a little bit more, and the work done in this case will be this shaded area. So frequently we will be using this convention where the final state will denote as if the pressure of the gas itself equilibrates with the pressure with the external pressure. So just try to remember these two differences. In the first case, the external pressure was slightly lower than the final pressure, and this we did because there are two pins adjusted, so the piston could not be moved further. Although the pressure of the gas was higher, it was forcing the piston to move, but it could not move because the pins were there. And if we remove it, then the gas will further expand, and it will expand up to a point when the pressure drops to the external pressure. And remember, at every stage we have to maintain this, since the gas is expanding under isothermal condition, the pressure is dropping along this line, which is the PV isotherm, which we got according to the Boyle's law. Now let us consider a case where the gas is compressed, or where we are discussing the work done associated for a single stage compression. So as before, we have a piston, but in this case it's a compression. So we have a mass, and the initial volume is suppose V1, and then we let the piston fall until and unless the pressure exerted by this mass is equal to the final pressure of the gas, which we denote as PF. Associated volume we denote as PF. Now how will you represent this entire situation on a PV isotherm? So just as before, let us consider this isotherm that the gas follows, because the gas we chose is an ideal gas. This is a pressure versus volume curve for a fixed temperature. Now here, think about it, initial volume was higher because we are talking about compression. So VI will be somewhere here. And what about PF? PF will be somewhere here, because the final volume is smaller than the initial volume. The corresponding pressures are PF, and here the pressure, the initial pressure was PI. So this is the initial state in this case, this is the final state. Because it's a compression, so the volume is going in the other direction, it is shrinking. Now let us try to understand what will be the work done in this case. Think about it. What is P external? As I said, that P external is making this compression, and the piston will fall until and unless this pressure of the gas balances the P external. So P external in this case is nothing but the final pressure. So the work done by definition is negative of P external into change in volume, which is in this case Vf minus Vi. So Vf minus Pi, the magnitude is still similar like the example we talked about. However, the external pressure here is higher, so the work done will be area under this curve. If you now compare what was the work done in the earlier case, let us go back. So in the earlier case, this was the work done. We went for a final state to an initial state, and in this case the work done, as you can see, is this. So work done for the compression is higher by the work done for expansion, which is this region. So we had a very interesting situation here. We said that we are going from the same initial state of the system. During the expansion, we started from some initial state of the system to some final state, and during the compression we did the reverse of this process. We went back, but what we saw that in that entire process, when we are expanding the work, the system worked as denoted by the shaded area. This is the work done by the system. However, when the compression was happening, the work done on the system by the surrounding was greater. So work of compression is always greater in magnitude than the work of expansion in magnitude at least. You see here that here Vf minus Vi is a negative quantity. So this entire thing should be a positive quantity according to our convention. Now what we just said is an interesting situation. We said that we started from an expansion. Say we put some mass here where the initial volume was Vi, and suppose then we expanded the system until and unless this thing expands and nicely balances this mass so that the final pressure is equivalent to the external pressure which is created by this mass, and the associated volume suppose is Vf. Now we are saying let us do the reverse process where we put a mass so that in this case a heavier mass so that the system actually comes back to its original position, which is Pi Vi for this mass. Of course, in this case the masses should be different. This was a lighter mass, that's why the system expanded, and this was a heavier mass. Let us call it as M1 and M2. So here what we did is that we just took out the M1 mass and put the M2 mass here. So since M2 was higher than M1, we created again more external pressure, so the piston moved down, okay, and we came back to the same initial state. Now this process is known as a cyclic process. Why? Because we started with the initial state and we came back to the same initial state for the system. So on the PV isotherm, what we are saying is during the expansion we started from P initial V initial, this state, to P final V final, to this state, and the work done by the system, which is a negative work, was equivalent to this. However, when we did the opposite process where we started from our initial state, remember, was this Pf. So this is process number 1. So this is work done in the process number 1, which is an expansion work. This is process number 2. So it's work done in the compression. So our initial pressure was Pf, note it down, and the volume was Vf, and our final pressure was Pi according to our notation, and the corresponding volume was Vi. So the work done was the opposing pressure into the change in volume. In this case the opposing pressure must be Pi, because as you see that Pi balanced the external pressure. So the area under the curve is this. So this is what I meant by work of compression is always greater than work of expansion for a single stage process, which means the system did not produce much work, but we had to spend a lot of work in order to bring back the system. Now there is a fallacy. The fallacy is, think about it, we started from this point for the system and reached here in the process in the change 1, and then we started from this point and we went back to the same position. So in this cyclic process, we did not change the state of the system. However, the state of the surrounding must have changed because we got some little work from the system, but we expanded more work on the system. Now, where is the fallacy? This cannot happen, which means the system has come back to its original state as if system has done nothing. However, the surrounding has spent more work because the net work gained and the work spent are unequal. So the net work produced by the surrounding to bring back the system is more. Now the fallacy can be resolved as following. Remember that there are two different masses, M1 and M2. So in this entire cyclic process, what we did, we lifted this mass M1 to a height, say h, and kept it there, and instead we brought back mass which is M2 by the same height. So the masses or the different masses or the altitude of different masses are now altered in the surrounding. So the lighter mass has gone up and the heavier mass has gone down, and that is the reason why we spent more work on the system to bring it back. So this is a very interesting example where we showed that we talked about a cyclic process. Initially we let the system expand, then it expanded, and then we compressed it where it came back where we started from. So the system has done nothing, but the surrounding has used the system to perform some work, some additional work. And what is that work? That work is basically lifting masses in the surrounding. In this case, we lifted a lighter mass and dropped a heavier mass, which means actually the surrounding has spent some work in this entire process. So these typical processes are known as cyclic process. We'll also consider other cyclic process in this course. Now let us move on and discuss how we'll represent the pressure volume work for a two-stage expansion process. By two-stage, I mean here that we'll do the compression in two steps which are in sequence to each other. Now as before, let us start. So we have a pressure volume curve, and then we are considering the expansion work. This is the isotherm, and suppose initially, remember that this is an expansion work. This is the initial stage. Let us denote it as the first stage as the state of the system for the initial state as P1 V1, and then we go to a state where the pressure is P2 and the associated volume is V2, and then you'll eventually go to a state where the pressure is P3 and the associated volume is V3. Now what does it mean? That means we had put a piston here with some mass, say M, and we let the system expand to certain stage. So in the first stage we remove these pins, and what happens here is that as soon as we remove the pins, the gas expands from an initial state P1 V1 to an intermediate state P2 V2, and then again we change the mass by some other mass so that the gas further expands, and the final volume is P3, final pressure is P3 and the final volume is V3. Now in this case, in the first stage, step number 1, what we did is the external pressure was nothing but P2, because remember that the pressure was reduced to P2, and that's exactly balance this external pressure created by the first mass M. So the work done will be P opposing, which is P2, into V1 minus V2. So work done in stage 1 is minus P external into delta V, and minus P external in this case is P2, and delta V is nothing but V2 minus V1. So this is represented by area under this curve. Similarly, if we further consider that in the second step, which is step number 2, the gas further expanded until and unless the pressure is P3, which balanced this opposing pressure created by the mass M prime, then the work done in step 2 is nothing but we are using the same formula, P external into delta V. In this case, P external is P3 times change in volume was V3 minus V2. So this is V3 minus V2, and this is P3, and this is P2. So the area under the curve is nothing but this, which is the work done. So the net work done, you can see, is this shaded area, this entire area. So what we learned? We see that if we had done in a single stage expansion, meaning if we had skipped this step 1 and 2 and directly gone from a situation where P1 V1 state is going into the gas is going from an initial state with pressure P1 and volume V1 to a final state with pressure P3 and volume P3, then the external pressure would have been P3, and then the work done will be simply the area under this curve, which we just discussed. So we see here that for a two-stage expansion we get more work than a single stage expansion, which is great, which means that we can increase the number of steps now to get more and more work. Now let us see how much work we can get maximum, or what is the maximum amount of work that the system can produce. In this case, of course, the hint is we'll make this number of steps as large as possible. Now let us see what we mean by that. So this is called a multi-stage expansion, where we are having the same situation. We have a piston with the initial mass that is holding this gas at P1 and V1, and this is the PV isotherm. And then what we are saying is that we'll reduce the mass by small amount. Say first we reduce the mass by very small amount, by say delta M. Let us assume that there is no pin here. So if I reduce the mass by delta M, what will happen? The external pressure will reduce a little bit, so the gas will expand to a point where the pressure of the gas is P1 prime, P1 prime. So this is nothing but M minus delta M. In the second case, we'll again reduce the mass by another delta M amount, so that the mass is now M minus 2 delta M, something like that. So the pressure will be even less, so the gas will further expand. In this way, if we proceed, this is known as multi-stage expansion, to the same final thing which we just discussed, which is say something like P3 or V3, whatever, with a mass which nicely balances that by say n number of reduction in the mass. So what will be the work done in this n step process? So what we are saying here is that this was the initial state, which was denoted by a pressure P1 and the corresponding volume V1. Then we reduced the external pressure by a little bit, such that the external pressure is now this pressure, suppose, which is P1 prime. So the gas will expand a little bit, which is this much amount. So the work done will be the area under the curve. In step number 2, this was step number 1. In the step number 2, what we are doing, we are again reducing the pressure a little bit, the external pressure. So the gas will again expand and do some work. So you can see overall, I will see a curve for the work done by the gas like this. So this is the same initial volume, say V1, and this is the same final volume V3. But now the area under the curve is very, very interesting. So this will be the area under the curve, which means now we have increased the number of steps and got much more work done by the system, which is great. Now this indicates that if we could do it by infinitely large number of steps, then we'll get the maximum work. What will be the mathematical expression for this work? So what we are saying is that in this case, the work done is nothing but negative of P external into delta V. In this case, I will use a differential notation because I am changing the volume by little bit amount, and then I have to integrate by the small work done for each change in the delta V, where the entire volume is going from V1 to V3, say. Now if we do that in a very small step, what we are saying here is that if I reduce this external pressure by a very small amount, which is delta P in this case, which is associated with the mass delta M, so then I can approximate that this reduction in the pressure will be always equivalent to the pressure of the system itself, meaning we are seeing the pressure dropping as if the system is adjusting the external pressure every time. So this external pressure will be nothing but the pressure of the system itself for every step. So we see the external pressure is nothing but the pressure of the system itself for each step. In other words, the system is nicely adjusting its pressure so that at every step the pressure of the system gets adjusted and equals to the external pressure. So we replace this external pressure by the pressure of the system itself, and now we can integrate, because this P is nothing but nRT by V, because as long as it is following the ideal gas equation, we can write that and then integrate from stage 1 to stage 2, and the result is nothing but minus nRT natural log of V2 by V1. So you see a very nice thing here. So this denotes the maximum work done by the system in an expansion work. Similarly, you can think of two-stage compression first and multi-stage compression first, where we have to spend less and less work as we increase the number of steps. Remember that in the single stage, we had an initial pressure, say in this case like P3 and volume V3. So this was my initial state. And then we'll go through an intermediate state where the volume is V2 and the pressure is P2, and then in the final state we'll go back to the pressure P1 and volume V1. So during this compression, the work done in stage 1, which we denote as W1, will be nothing but P external into delta V. And what is P external here? P external has to be P2 here, because remember that the gas is now compressed until and unless the pressure equals the external pressure equals the pressure of the system. So the pressure of the system is changing until and unless it nicely balances to the external pressure. And in the second stage, the external pressure has to be P1. So the work done will be nothing but the addition of these two areas. So this is for W1 and this is for W2 for the two-stage compression. Note the striking difference if we had done it with a single step going from P3 to P1 V1. We would have set the external pressure P1 right away in the beginning, and the work done by the surrounding on the system would have been this area under the curve. So we see just the opposite effect of expansion. In the expansion case, we are getting a minimum work in the single step, and moment we increased the number of steps, we saw that we are getting more and more work. In this case, if we do a single step compression, the work done on the system was much more, and then moment we change it to a two-step, we see the area is now lessening by an amount this. So in the same token, if we keep on increasing the number of steps, the work done on the system by the surrounding must be less and less. Let us just try to draw that. What will happen for the multi-stage compression? In this case, remember that we have to increase the external pressure every time. So just in the same token, we have to increase the pressure a little bit so that the gas is compressed. So the gas will get compressed until and unless it reaches equilibrium, which is at this point. So the compression in the first step will be like this. Compression in the second step, if we increase the pressure this much in the second step, will be like this. So the work done will be a summation over all these areas, and if we reduce the number of steps, it will look like something like this. This was P1 and this was P3. So we see that we can actually have the minimum work done on the system for the compression if we do it in a multi-stage way, where the number of steps is infinite. As before, the expression of the work done will be similar, that I'll have the external pressure into little change in volume, so I have to integrate from 3 to 1. So ultimately I'll get the same expression nRT ln, but in this case it will be V final minus V initial, so it is V1 by V3. So what we learned is that if we do a cyclic process in this case, where we first did a multi-stage expansion and then did a multi-stage compression. The work done for the expansion is nothing but minus nRT ln V3 minus V1, where this is V1, this is V3. So this is the work done by the system because this is expansion. And when we do the compression, we do exactly the opposite thing, where the work done will be minus nRT ln V1 by V3. Now note that in the expansion case, we drew it like this, so the area is slightly less than the compression case, because in the compression case we have to increase the pressure a little bit for every step. However, in the limit of very large number of steps where we approximated the external pressure or the pressure of the system to be adjusting with the external pressure for every stage, then for both compression and the expansion, it will be just the area under the PV isotherm for that change in volume. So we see that we can get the maximum work for expansion by the system or the minimum work for compression by the surrounding on the system, and these two magnitude nicely cancel each other. So if you do a cyclic process like this, then the work done by the system exactly cancels out the work done on the system. So the system comes back to its initial state, the surrounding also comes back to its initial state. So such processes are known as reversible process, where as if we have done nothing, we have just moved along this isotherm when we did the expansion, and we went back along this isotherm when we did compression. So both the states of the system and the surrounding in this particular cyclic process are restored, and such processes are called isothermal reversible process. So to summarize what we discussed today, we first discussed what are the terminology, for classical thermodynamics, where we defined many terms such as system, surrounding, what are open, isolated and closed system. We gave examples to each one, and then we moved on and first discussed the zeroth law of thermodynamics, which basically talks about the systems in thermal equilibrium and gives a concept of temperature. So the zeroth law is nothing but a law of thermal equilibrium. Then we focused on particular process where we talked about expansion and compression work. In the expansion case, all this work are known as basically pressure volume work, and we talked about the expansion work and the compression work. So the expansion work, remember that here the system works, so by convention we call it as a negative work, and for the compression work, the work is done on the system, we are taking it to be positive, and for that we defined the work done as P external with multiplied by the change in volume with a negative sign. If this volume change is finite, we use delta V. If this volume change is very small, then we write it as in the differential notation and integrate over the entire process. And we also discussed what is a single stage expansion. We got that this corresponds to minimum work from the system. Similarly, we talked about single stage compression, and we showed that we have to spend maximum work by the surrounding on the system. Then we talked about multi-stage, and we showed that in the very large number of stage, if this number of steps is infinitely high, then the work done during the expansion by the system and the work spent during the compression by the surrounding on the system will be equal, and this work will be nothing but the area under the pressure volume isotherm. In this particular case, we took the example of an ideal gas. So we asserted that at every finite step, which is very small, which is infinitely small step, the pressure of the system is getting adjusted to the external pressure, because in this case the external pressure is changing by infinitesimal small amount, so that the system pressure is also adjusting to it during the expansion as well as during the compression. So the both work magnitude wise will be equal, and for a cyclic process we'll come back wherever we started for the system as well as for the surrounding. For the single stage case, we come back for the cyclic process, we come back for the system, but the surroundings are not restored to its initial state, and we saw that it spends more work, and it was explained that this more work was done because we lifted some masses in the surrounding. So in the next lecture, we'll discuss more on this, more on the cyclic process, and we'll discuss first how we can develop the concept of the first law of thermodynamics from this discussion. Thank you.